Welcome back, everyone, to the eCoreAcademy e-learning platform today. My name is AJay Raj, back with another geometry video for you all today. And before we jump into today's video, please make sure to smash that subscribe button down below, hit that like button on this video, as well as hitting that post notification bell to get notified on any of our channel's latest posts. Our lesson for today, our geometry lesson, is all about algebraic proofs, and the whole topic of today's lesson and theme of today's lesson is to discover what are the common algebraic proofs used in geometry and how are they utilized. So I did a previous video on two-column proofs, geometric reasoning, as well as geometric proof, going over the basics and fundamentals of proof in geometry. So I highly recommend you at least watch my proofs video on geometric proofs before jumping into this video here, because I do refer to some topics that go along and correspond with that video. But all in all, algebraic proofs, if you can't tell already, are a form of proof. It's your most popular form of proof that you're going to actually use in geometry. I know it says algebraic. You might be thinking of algebra as a separate topic, but algebra ties into geometry very heavily. It's a very good form of representation, and a lot of its properties and proofs can actually be utilized to further prove or give reasoning for geometric processes. So let's jump right into it. Let's identify what these proofs are, what these common algebraic proofs are, and then I'll show you some practice problems and some applications to see exactly how they're utilized. Let's move into it. So let's look at what algebraic proofs are as a whole. So the concepts of equality is what this whole slide is about. So let's look at the definition of algebraic properties, which is another way of saying proofs. So algebraic properties are the addition, subtraction, and division properties of equality using real numbers to balance equations. So if you don't already know what proof is, it's a form of reasoning for any geometric process. And you can use properties, you can use methods, you can use previously proven concepts as proof, but in algebra, for algebraic proofs, it's specifically known as algebraic properties, and these algebraic properties are used as proofs in the form of algebra. So like I said, algebraic properties are the addition, subtraction, and division properties of equality using real numbers to balance equations, as well as multiplication. I forgot to add that here, so I apologize. So it's as well as multiplication. So I'm gonna label all of these here. So it's going to be multiplication. I'll label them down below so that you guys aren't confused with what I said. So it's going to be addition, subtraction, multiplication, and division properties, which are your four basic properties of equality, and you're using real numbers to balance equations. So in algebra, the whole essence and goal of algebraic equations, if you haven't already known, and you were expected to know this coming into geometry, the whole form and property of algebraic of algebra in general is to actually balance an entire equation. Therefore, the algebraic proofs that we will be getting into today will exist of equality properties and not congruence properties. So when you're looking at an algebra equation, say for example it has a variable on one side. I'll just show you an example here real quick. So say for example we have 25x plus 10 equals 60. Well, the whole goal of this equation is to balance the equation, meaning you're going to maintain equality to find the actual value of your variable, x in this case. So you're going to try and balance the equation, and you're going to try and maintain equality all throughout the equation. So these properties that are going to be based off of algebra are going to be equality properties. These are ways that you can balance an equation by adding the same property to both sides of the equation. And because of that, algebraic proofs that we will get into today will exist of equality properties, and the reason that they won't be congruence properties, although equality and congruence mean similar things, equality has to do with balancing equations in general, but congruence has to do with figure properties, meaning figures being congruent or angles being incongruent, those type of things. And I'm just going to write this down here, and I'll say and multiplication, so that you guys don't get confused. And multiplication. All right, let's move on to the next slide. So let's get into what exactly these algebraic proofs are. So this is just going to be informative. I'm going to be taking you through each and every one of these basic and main algebraic proofs that are often referred to in geometry, and then we'll try and put them into problem formats so that we can actually derive the solution. So let's get into it. So our first two properties are the reflexive and symmetric properties. The reflexive property of equality, it basically states that A equals A, meaning if you're given a value, any representative value here, say for example you're given the value of 8, and you're saying that 8 equals 8, correct? That means you can swap this equation around, meaning you can move this 8 here and you can move this 8 over here, and that will still maintain equality. So very simple equality statement right there. And then our next property of equality is the symmetric property of equality, and it states that if B equals A, then A equals B. It's very similar to the reflexive property of equality, and that's basically saying that two values that are equivalent to each other can always be swapped and can always be interchangeable because they're always going to maintain equality, and that's a property of your equal sign. So that means if you're given the value, say for example 6 equals or let's put this in the form of variables. So let's do, like I said here, let's do another example. So say, for example, we're saying 25x equals 15y. Well, since they're both equivalent, you can always swap these two values around to 15y equals 25x, and that'll always be the same. That'll always maintain equality and always be a true statement. So these are fairly simple. The algebraic properties you should already be acquainted with. I'm just going to go over this as more of like a review and try and put them in terms of geometry, just to try and get you acquainted to a bit of a transition. But I will be trying to roll through these pretty fast. This should be a very short lesson for you all. So I'll just recap on these properties of equality. So we're going to move on to our part 2 of algebraic proofs, and the two properties that we're going to look at here, the next two, our third and fourth ones, are the transitive property of equality and addition properties of equality. So transitive and addition properties of equality. So our transitive property of equality states that if A equals B and B equals C, then A equals C. So in layman's terms, what that is, I've already referred to this previously, the transitive property of congruence, but I'll just recap here. So you're saying if value A equals value B, so you're saying if two separate values equal the same exact value, then they're both equivalent. So what that's saying is, say for example, we could say 25x equals 5b, we'll say that, and 5b equals c. We know that since 5b equals 25 and 5b equals c, that means c must also be equivalent to 25x, because you can substitute 25x into this equation to state that they're both, that it's going to maintain equality and that it will always be true. That'll always be true. And then I'll clear this out here. So you can always change this. I'll rewrite this here. So you can always swap these two. You can always swap these two and it'll maintain equality. And then our next one is addition property of equality. A very basic equality statement says that if A equals B in an equation, if A equals B, then A plus C equals B plus C. So that what that's basically saying is, if you add the same value to both sides of an algebraic equation, then it'll always maintain equality. So it's saying, say for example, we're saying that 25 is equal to 25. If we add 5, say for example, we're going to add 5 to each side, it's going to state that 30 equals 30, which means that this equation will always be true. So it's very simple equality statement. Now we're going to move on to algebraic proofs part 3. This is our subtraction property and multiplication property of equality. So the subtraction property of equality, basically the inverse of addition. So the addition is your main concept here, and then subtraction is the inverse of that, just as multiplication is your main property given, as division is the direct inverse, and that's vice versa. It can be swapped any way that you want. So subtraction property of equality is basically just the inverse of that. So subtraction property of equality states that if A equals B, then, sorry, this is incorrect. I apologize. If A equals B, then A minus C equals B minus C. So all you're doing is you're taking that original equation, the addition property of equality equation, which is A plus B equals B plus C, and you're just basically subtracting now. So what this states is that if you subtract the same value from each side of the equation, you will always still maintain equality. So I'm going to put a little example here. Put an example over here so that you guys can see what exactly I mean. So say for example, we're saying that 25 equals 25. And what if we subtract, I don't know, let's subtract 10 from this. So we have to subtract 10 from both sides of the equation. And since we do that, we're going to get that 15 equals 15, which is going to always be true. So this equation is always going to be true, which proves that the subtraction property of equality is always accurate for any algebraic equation. And our next property of equality, we have the multiplication property of equality, and that states that if A equals B, then A times C equals B times C. So all you're doing is you're going to add, use a property of a variable, and you're going to add that to both sides of an equation in any aspect, in any balancing part of an equation, and you're always going to maintain equality. So that states that if basically if you multiply the same number on same value on both sides of an equation that are both equivalent, then you're going to maintain equality as well. So if I were to say, I'll use 25 here. So if I say that 25 equals 25, and I multiply each side by 2, we get that 50 equals 50, which is always going to be a true statement, always. So that proves the multiplication property of equality. And I use asterisk for a keyboard format, but this is how it looks like in regular format. So AC equals B times C. There we go. Let's move on to our final property of equality that I'm going to mention today, and that's our algebraic proofs part 4, and this is the division property of equality. So this is basically the inverse of the multiplication property of equality. Just as I said, subtraction property of equality and addition property of equality, as well as their main properties, are both going to be inverse operations. The multiplication will be an inverse of division because it reinstates the exact opposite property to an equation. So the division property of equality states that if A equals B, then A over C equals B over C. So just as the multiplication property of equality, you're multiplying the same factor to both sides of an equal equation, and you're balancing them that way to maintain equality. Division property of equality does the inverse of that, but it will still maintain equality, and you're dividing each side of an equal equation, both sides of it, by the same value, which is in this case C. So if we take our example here, 25 is our value here, and we're saying that 25 equals 25, which is always true. We're going to divide each side by 5, since we have to keep our value that's being divided the same constant, which is C here, represented here. And since if we calculate that, we get that 5 equals 5 after simplification of this balanced equation, and we can see that this is always going to be true, since 5 does indeed equal 5, which proves our division property of equality. So let's move on to the application of algebraic proofs. So let's look at the two-column proof. If you don't already know what the two-column proof is, I will give you a little recap here, but I did do a whole entire video on the type styles of proofs, and I went largely over the two-column proof, so I recommend that you view that video. If you need it, I will link it down in the description, just in case if you want to look at that and refer to that, but I will give you a little bit of a recap here. So the properties of equality can be utilized as proof statements, like I said at the beginning of the video, in a two-column proof, which is a style of proof. It's a form of proof in which you can state, you can take a geometric process, such as an equation, and you can break it down into little steps, and on your other hand, right-hand side or left-hand side, opposite side from that, you can explain, give reasoning for that. And these properties of equality are very important because they can be utilized as proof statements in a two-column proof when providing reasoning for a step in an algebraic process. But algebra is also incorporated in geometry, so it can also be a geometric process in the form of algebraic terms. And it will always be in the form of an equation. Like I said, this is all about balancing an equation and equality. So that's what algebra is all about in this form. So it has to be through an equation. It can't be necessarily through a figure, because then that would have to be congruent statements, and I will explain that in a later video. Probably our upcoming video after this one, or 2 videos after this one, I will be explaining that. And this is basically what a two-column proof looks like. It's split into 2 sections, one being the statements and one being the reasons. And this is basically steps of your equation, steps of process. And then this one here, this column here, is going to be proof. So it's just your proof for every step. And without proper proof in geometry, any step that you're taking will not be considered valid, or it will be marked wrong. So proof is very important in geometry. It can be very tricky, but that is exactly what I specialize in. So you guys are in it for a good knack to get out of this and all of these topics. So I'll teach you neat tricks to memorize these proofs and how to actually adapt them into real-life applications and applications in geometric problems. And we're going to move on to our next problem here. It's going to be practice with two-column proofs. So this is our part 1 of this. I'll have two separate problems for you to look at. So I'm going to make a little two-column proof here with my two lines separating, and one side is going to be my statements and the other side is going to be my reasons. So let's start off with this equation here. So we're given this equation 25x plus 10 equals 60. So I'm going to write given since this is a problem. Whenever you're given a problem and you're just restating in a two-column proof, you're just going to write for the reason given because it's what's given to you already. So you don't have to prove that. That's given here. The next step of the equation is 25x equals 50. So as you can see here in this equation, we lost the value. We lost 10. So what we did was we subtracted 10 from each side of the equation to try and maintain equality and try and simplify it even further. So if we subtract 10 from both sides, we get 25x plus 10 minus 10. I'll just write this down here. 25x minus 10 equals 25x equals 50. And since we're subtracting the same value from both sides and maintaining equality, this will be a subtraction property of equality. So subtraction property of equality. And for our last step, we basically simplify this equation to our last bit, and we're trying to simplify for the variable x, and we isolate that term to get that x equals 2. And what we did here was we divided 25 from both sides to simplify for x. And since we're dividing the same value from each side of an equation to maintain equality and balance the equation, we get that this is the division property of equality. So division property of equality. I'll just draw a little arrow so that you know exactly what I'm pointing to. And now we're going to move on to our final problem, which is Algebraic Proofs Practice Part 2, and this is going to be more practice with two-column proofs. This is going to be a very simple proof, two-column chart, and I'm just going to apply the transitive property of equality. So I'm going to make my two-column chart here. I'm going to put my statements on my left side and my reasons on my right side, and then we're going to give our first statement here, and that's prove that the value of variable c equals a. So we're going to write here that that's a given statement because it's been given to us already. And I'm just going to swap colors here real quick. There we go. And since we're just going to prove that here, and since we're already given that value here as is, we're going to just say that it's a given value since it's given as the problem to us. And next step is that we're given that c equals b. So that's also another given statement here since it's given as part of the problem, information that we're already receiving. And we're given that c equals b. And next we're given that a also equals b, which is also a given statement. So finally, we're going to have to prove this last step here, which is going to be our conclusion of our statement, which is a equals c. And since we can see here, this is a very thorough process that describes the transitive property of equality. Since it's saying that c equals b, and since a also equals b, that means a must also be equal to c, which just exemplifies our transitive property of equality. This is just a stretched out form of the equation itself. I was just trying to show you how they actually derived the equation of the transitive property of equality. Let me just fix that real quick. All right. Transitive property of equality. Alright guys, so that'll be it for today's video. Hope you guys enjoyed. This has been the eCoreAcademy e-learning platform today. If you're watching this through YouTube, please make sure to like and subscribe down below and hit the post notification bell to get notified on any of our channel's latest posts at eCoreAcademy. And visit our website please at www.ecoreacademy.org with this link right here, and we'll also have the link in the description down below, the full link, full access to it. And what we give in our website, well that's what do we give in our website? We give full unlocked access to all of our content, which includes organized course studies with all of our courses and all of our videos shown here on YouTube, as well as accessible notes, integrated quizzes, and worksheets that go along with each and every single video, as well as our own support, as well as information there that's all extended to you with all of our events and all those specific details. Feel free to email us at eCoreAcademy@gmail.com if you have any questions like about our website at eCoreAcademy.org, or if you just want to reach out to us. And please visit all of our socials down in the description box below, which is Facebook, Twitter, and Instagram. We have all of our links down there. And check out what kind of content we have there. And you can even share all of these videos if you like to those who might need help or those who might find it interesting. So once again, guys, I hope you guys enjoyed this video. It's been AJay Raj, and I will see you guys in the next one. Peace.